Okay, so here's the step we're at. We've recovered our sediment core, we've processed it, we have recovered our environmental proxy, in this case a whole series of different fossils. And what we want to be able to do is we want to be able to translate this depth below the surface, as recorded in the core, to an absolute age. So the first thing we can actually do is take a relatively simple scenario, which would be to assume that we have a constant depositional rate. We could therefore take one point, say, near the start of the core, one about halfway through, work out via some mechanism the age of each, and then extrapolate for the remainder of the core. Now that's clearly a significant assumption, potentially an over-assumption, and a scenario such as this, for example, could very well apply, where while the age can be calibrated between here and here, the first and the second of these two triangles, if we extrapolate the whole way down, we may ignore the fact that a change in the depositional rate has occurred with depth, and as a result of that, the third age that we get is at a much shallower depth than we've predicted, because in the older part of the succession, this interval here, for example, the deposition rate was much less. So we end up with the same thickness as in interval 1, but it actually accumulated over 3 times as long. So in short, the relationship is not constant over time, and it's almost certainly the case in most depositional sequences that applies. So ideally what we're going to want to do in any scenario, and however we choose to date these sequences, is we want multiple age depths through our succession. Now there are a whole variety of absolute dating methods available. Some are more relevant to younger sediments, others are used for geological samples from deep time, and we're just going to look at a few of them. The first I want us to look at then is dendrochronology, which, as the name implies and as the image confirms, is using the tree ring widths in order to establish a chronology. And the principle of that is shown in this slide, where what you do is you establish, for example, with your base as a living tree here, giving you right up to date, a series of tree ring widths, and then you find in older examples where that pattern of tree ring widths overlaps between one sample and the next, and over time you can build up a continuous record. Now there are a couple of complications that you should be aware of. For example, in a single tree, the growth rate can vary through its life. It tends to form broader annual rings in younger trees, and therefore the absolute width may differ if the overlap that you're trying to compare is between the older part of one tree and the younger part of the next. Second thing I also want you to be aware of is that the variation in tree ring width can also yield environmental data, and that's dendroclimatology, which is distinct from dendrochronology, which is using the actual tree ring width as a dating tool. And that variation in tree ring width that you see can actually be also analysed and put in a temporal framework by looking at the chemistry of the wood through time. The absolute dating method that we're going to focus on most is radiocarbon dating. Carbon-14, coded as 14C, as you see here, is a weakly radioactive isotope of carbon, and it has a half-life of around 5,730 years. In practice, for historical reasons we needn't go into, when actually doing radiocarbon dating, a slightly different half-life is used. So what we do is we measure the discrepancy in the ratio of carbon-14 to carbon-12 that you get in your sample, and that in the biosphere. And the data is reported as years BP. So for example, 1950 AD is the baseline, and that's taken as 0 years BP. So here's our scenario simply shown diagrammatically. We start off with 100% of the radioactive carbon after 5,700 or so years. We've reduced that amount by 50%. It's actually converted by beta decay to nitrogen-14, and therefore the daughter isotope has increased from 0% to 50% over the same interval of time. So carbon-14 is formed in the upper atmosphere by the effect of cosmic ray neutrons on nitrogen-14 atoms. It's oxidized while in the air to form CO2, and it's then distributed globally in that form by stratospheric winds. We lose a lot of the carbon-14 at the surface of the Earth into the oceans, but usefully for us, around 1 to 2% of it enters the biosphere, principally via photosynthesis, and it thus enters the food chain. So metabolic processes in living organisms maintain the carbon-14 in approximate equilibrium with the content found in the atmosphere. Now, critically, carbon-14 does decay in living tissue, but is continuously replaced by biochemical processing of plant or animal tissue. But it's at the end of the metabolic processes, in other words, with death of the organism, whether it's a tree or an animal, the amount of carbon-14 then begins to decay and is not replaced. So what we've started then is the process by which we can actually date this based on the radioactive decay. Now, most organic compounds can be dated. It's very common to use, for example, plant material, wood, for example. Some inorganic material can be used. Aragonite, which of course is a polymorph of calcium carbonate, mix up certain types of shells. But the key thing here is that the formation of that mineral must have involved the assimilation of carbon-14 in equilibrium with the atmosphere. Many organisms display what's known as a vital effect, whereby the minerals they precipitate are not in isotopic equilibrium with the sources. Historically, the older method of calculating a radiocarbon age was decay counting. So as the carbon-14 nucleus broke down and emitted negatively charged electrons, these beta particles were picked up on scintillation detectors, and then the count rates for that sample were compared with a standard of known age. And that process was limited to material of, at the most, of about 40 to 50,000 years old. The limitation, of course, with that is that the accuracy of the method was impacted on by the fact that relatively few atoms would decay in the course of a typical detection period. Now, the field of radiocarbon dating has been revolutionized by the use of accelerator mass spectrometry, or AMS, and what it does is counts the absolute abundance of the two relevant ions that we're interested in, carbon-14 and carbon-12. So the ions are liberated from the material under investigation and accelerated to high velocity before mass analysis, and that acceleration enhances the separation of the rare isotope, the carbon-14, from the abundant isotope, carbon-12. And we have much greater detection efficiency, which makes it possible to use smaller sample sizes and smaller counting times. It also opens up the possibility of actually analyzing materials that have low carbon content, for example, bone. So it becomes very important in things such as archaeological analyses. And ultimately, current work in progress may extend the dating time up to about 100,000 years using this methodology. So there are a number of assumptions we have to make in radiocarbon dating. The first is, of course, that our instrumentation is capable of measuring the natural levels of carbon-14 accurately and precisely. We need to be very cognizant of the risk of contamination from other sources. And of course, we need to make sure and be confident that our samples have integrity. For example, that Diogenesis has not overprinted the carbon-14 to 12 ratio that has occurred as a result of the age of the sample. We also need to make sure or be confident that only beta decay of the carbon-14 has occurred after death, and that's the sole reason that the carbon-14 to 12 ratio has changed over time. We need to make sure that the complete and rapid mixing of carbon-14 has occurred through each of our reservoirs globally, otherwise we're not got the same starting signal whenever we compare two samples from different spatial regions. We also need to be confident the carbon-14 to carbon-12 ratio in materials of zero age is similar in each of our reservoirs, and any isotopic fractionation, for example, as a result of biological processes, has been identified and has been factored into our analysis if relevant. And we also need to test the assumption that the carbon-14 to 12 ratio in materials of zero age has been constant over the whole carbon-14 timescale. So let's look at some of these assumptions a little bit further. And really this is to demonstrate to you how complicated some of these mechanisms for absolute dating are. So let's take the concept of isotopic fractionation first. There are three natural isotopes of carbon, 14, 13 and 12. Of course, carbon-14 is the radioactive one. Plants favour the lighter isotope. So in other words, they will take up proportionally less of the heavier isotope, carbon-14 especially, and also carbon-13, than is in the reservoir. So the result of that is isotopic fractionation, the scale of which will depend on the specific plants you're talking about and their biochemical pathway. But the key is that that difference, that discrepancy between the ratio that the plants take the isotope ratios up in and the original reservoir is actually then contained and passed along the food chain, and in fact it's actually made worse by further fractionation at higher levels in the trophic chain. And the process for correcting for isotopic fractionation of this matter is known as normalization. And what these images here are trying to show that. So if we take our three isotopes, for simplicity I've shown them as being equally abundant. If our plant absorbs those, it will favour, for example, the lighter isotope that you see here and discriminate against the heaviest of the isotopes, and that fractionation effect then passes through successive levels in the food chain, becoming significantly more exacerbated in the process. Similarly, our radiocarbon dating in first principles depends on the carbon-14 to carbon-12 ratio in materials of zero age being similar in each reservoir, which is now known not to be the case. So, for example, we have what's known as the hemisphere effect, which is where the atmosphere circulation systems in the northern and southern hemispheres are strongly independent of each other, and there's a time lag in mixing between the two. The greater ocean area in the southern hemisphere means that the atmosphere carbon-14 to carbon-12 ratio is actually lower in the southern hemisphere. And there's also a reservoir effect, which is known from both marine reservoirs and also freshwater systems. Here, for example, I'm showing diagrammatically the marine reservoir effect. And what that means is that you will end up with a difference in the radiocarbon date that you derive for samples of the same age between the terrestrial and the marine environment. If we take land plants, the carbon here is largely sourced directly from the atmosphere, and that then is passed upwards through the food chain. But the source in marine food chains is the ocean itself. And what happens here is that ocean circulation returns deep water, which is often of considerable age, back to the surface in upwelling zones. Now, this deep old water has experienced carbon-14 decay from the time the carbon-14 was input in the atmosphere through to the time it comes back up to the surface in the upwelling zone here. So what you're doing at this interval spatially is mixing old water with young water, and it compromises the carbon-14 dates that you then derive from samples that form in these settings. Likewise, the carbon-14 to carbon-12 ratio in materials of 0 age has not been constant over the whole of the carbon-14 timescale. I've picked out some of the key variables that impact on this. There's what's known as the Suess effect, which is how we'll refer to it as. It's also called the industrial effect and the Autobahn effect because it was first detected from samples collected near motorways in Germany. And ultimately, the cause of it is the fact that once you use fossil fuels and release the CO2 into the atmosphere, you're releasing carbon that has minimal or no carbon-14 content because it's geologically old. You can get some insight into the scale of the problem when you compare how much carbon is released by this mechanism compared to how much carbon-14 is produced annually by cosmic radiation in the upper atmosphere. Now, the absolute numbers don't matter here, but you can see that the first of these far outweighs the second. The second variable I want you to be aware of is what's known as the Libby effect or the atomic bomb effect, and this dates back to the detonation of thermonuclear devices in the atmosphere in the middle of the 20th century. And what that did was it generated huge quantities of artificial bomb carbon-14, and in fact between 1955 and 1963 the amount of carbon-14 in the atmosphere almost doubled. We also have what are known as de Vries effects on short to medium term. Every 100 years or so we seem to have anomalies in the production of carbon-14 in the atmosphere. For example, there are peaks at around 1500 and 1700 AD. So these peaks and lows are occurring in response to solar activity. When solar activity is high, carbon-14 production is suppressed, and that's because of the shielding effect of the solar wind against cosmic rays. On longer time scales, we also have a variation in carbon-14 that's linked to the intensity of the Earth's dipole magnetic field. And that's because the greater the strength of the magnetic field, the more attenuated the cosmic flux to Earth is. Now we can actually look at some of these effects diagrammatically. So here we have carbon-14 abundance above modern day environments plotted on the y-axis against time for the last century or so. You can see that we've divided this up into two parts. Here we have what's known as the Libby effect, and before it we can see a scenario whereby the Suess effect is displayed. So what you'll see is that the addition of the dead carbon in response to the Suess effect depresses the carbon-14 content. What we've done is we've flooded our system with dead carbon, so our relative proportion of carbon-14 has been suppressed. On the other hand, here, with the addition of all the artificial bomb carbon-14 in the middle of the 20th century, what we've done is actually elevate the carbon-14 content. So you can see that these two variables, of course, are actually going to pull in different directions. The addition of dead carbon suppresses the carbon-14 content, and the addition of the bomb-14 carbon pulls the levels of carbon-14 upwards. And that's what I've tried to show diagrammatically here in a simple sketch form. If we took our scenario where we had a proportion of dead carbon and a proportion of carbon-14 carbon, the Suess effect will add more dead carbon and thus depress the carbon-14 content. The artificial bomb content floods the system with carbon-14 carbon and thus depresses the relative amount of dead carbon. If we take this plot here, we have a line running from the top left corner to the bottom right corner. What this is saying is that if we have a sample that has a 0 age for carbon-14, that sample formed in 1950. If on the other hand we have a sample that is a carbon-14 age of 300 years old, that sample formed in 1650. But what you'll notice is that our actual plot of the carbon-14 age through time is not linear. In fact, it is significantly sinuous. First thing we'll look at is this interval over on the right hand side from about 1890 onwards. And what you'll see here is that we have a significant and steady upward trend as the Suess effect becomes very pronounced, reflecting the scale of industrialization from around this interval onwards. And then if you look at this part of the graph over here, you'll see that it oscillates, and this is expressing some of the de Vries effects. There are others that are older in time, of course, and these oscillations in carbon-14 result from changes over time in the level of solar activity. Deviation from the perfect correlation is not as straightforward as consistently being more carbon-14 than we would predict or less carbon-14 than we would predict. We're going to link carbon-14 abundances in the atmosphere with solar phenomena, and in particular we're going to link it with the idea of changes over time in the average sun surface temperature. Sunspots are actually areas on the surface of the sun that are cooler than the average temperature of the sun, but these dark spots are accompanied by rings that are brighter, corresponding to hotter, known as faculae, and the latter more than offset the reduction in temperature caused by the spot itself. And typically these sunspot cycles are arranged in a very irregular 11-year cycle. However, what you have on a longer time scale are intervals whereby sunspot activity is either depressed or elevated. For example, you can take something such as the Maunder minimum from around the 1650 to 1700, so the later part of that century, and this is an extended interval in which sunspot activity was low. So this is variation superimposed on any 11-year irregular cycle, and that's variously suggested to be the cause of what's known as the Little Ice Age. But it's also interesting to try to link some of these solar activity events as an explanation for how carbon-14 has fluctuated through time. So, for example, if we take the interval from around 1600 onwards that we looked at previously, you can see that here we have our plot of sunspot activity modelled, and here we have a plot for radiocarbon abundances. And you'll see firstly that the abundance of radiocarbon is increasing in this direction, so this increase here corresponds with depressed solar activity, as you see here. Likewise, this decrease in carbon-14 here corresponds with this increase in solar activity as expressed in terms of the sunspot number. And then if we look at the latter part of this plot, you can see that unlike the former part, we get a little bit of deviation as to how the sunspot activity and the carbon-14 flux behave. So what we're doing here, of course, is this is the addition of the Suess effect. The Suess effect corresponds to the addition of large volumes of dead carbon, and the result of that, of course, is to drive down the relative abundance of the carbon-14, and as a result of that, then we see the trend from positive to negative numbers in terms of the abundance of carbon-14. One final point about radiocarbon dating. This line here, remember, shows that if the carbon-14 to carbon-12 ratio was in materials of zero age was constant over the whole time scale, the relationship would be invariant, and 200 years BP would correspond to 1750, 100 years BP would correspond to 1850, and so on. But in fact, if our sample returned a carbon-14 age of 200 years BP, plus or minus, say, 20 BP, which corresponds to the shaded area, what you can actually see is that that potentially will intercept the calibration curve at 3 different points. And what's happening here is the deviation from the sole time at which it cuts the calibration curve is a function then of the variation that's induced by things such as the De Vries effect, and over here on the right hand side the Suess effect. And collectively these effects then preclude us assigning a single finite calendar age to our data set. So we would have to resolve what age that was by an independent means of eliminating 2 of the 3 options. Now, the calibration to account for how carbon-14 has fluctuated over time has used tree rings. So the chronology of these, remember, can be established by counting the rings backwards, and then calibration between different trees extends the record even further backwards, and that allows us then to collect samples for which the carbon-14 can be determined that are of a known age. And as a result of that, then we can actually plot up the sorts of curves for the chronologies that you've seen in the previous images.